This is the first set of notes on the topics that we have yet to cover that are going to be included on the AP Calc BC exam. The information we've yet to cover is on a topic in calculus called differential equations. Differential equations are equations that relate the derivative of the function back to both the x and the y coordinate. So note that differential equations are super important because they are used to model like almost any dynamic system, dynamic meaning system in motion. On the screen here are a bunch of like physical systems that are usually described by differential equations. Anything where the rate of change is directly related to the original position or the initial conditions. So, like for instance, in physics, a differential equation you've maybe know all about but haven't really thought of as a differential equation is just an object falling, where the acceleration is just constantly 9.8 meters per second per second. Or the second derivative of this object's position is constantly 9.8. But there are plenty of other examples that you may or may not recognize. Drag coefficient in of a falling object, or the acceleration of an object or the force of an object in a spring, better known as Hooke's law, can be thought of as mass times acceleration, or mass times the second derivative of position, is equal to a constant times how far out of equilibrium this object is. And other examples as well that are fairly common and you can see as well. But differential equations are some of in terms of engineering and otherwise, some of the most important sorts of equations that applications will use. We're going to look at a special class of these things called first order differential equations. A first order differential equation, as you might guess, involves the first derivative of the function. This notation here, we're going to see quite a bit. This f of x comma y, this is in g of x comma y. This is notation that means we're talking about a function that's got both x's and y's in it. And in this case, first order differential equations are maybe a function with x's and y's plus the derivative of this original function y times maybe something else. So often this f of x comma y is just a constant like 1, or maybe it's more complicated than that, but it's something times the derivative plus something else, and we always rearrange that equation to be equal to 0. You may or may not have solved some relatively simple differential equations last year in AP Calc AB. If you have, great. If not, we're going to review a bunch of techniques in the coming days here that will help along with this. Okay, here's an example of a first order differential equation. The derivative of this equation, dy dx, minus 3 times y is equal to 3. So this derivative, this is an equation that's got both a derivative and a point somewhere in here that is, they're dependent on each other. And in this case, we're saying the derivative minus 3 times the original function is just equal to this constant 3. Eventually, we're going to see some techniques for how we could solve to figure out what this actual function y is in terms of x, but we're not too worried about that at the moment. In this example, there's in fact a proposed solution to this equation. And part A says we want to show that this general solution, that this equation is a solution to this differential equation. And note that the c is some constant that's yet to be determined, and we will eventually determine that based on some initial conditions. So I'd like to try to work out these 4 examples for you here. Please bear with me. I'm experimenting with some new technology here, so I'm going to try to actually write on this document. My handwriting might be even worse than usual, but hopefully I'll get better over the course of the time here. So I want to show that this equation is a solution or this equation is a solution to this differential equation. The most easy way, if you have a proposed solution, is to substitute this solution into the differential equation and show that the differential equation itself is balanced. So this tells me that something I definitely know about this is that if I know this function, this proposed solution y, then something I can definitely do is I know how to find its derivative. So let's see if I get this a to stick. So if I know that y is in fact equal to c times e to the 3x minus 1, ooh, that's pretty bad. 3 to the cx minus 1, maybe we'll get a little bit better handwriting that, minus 1, that's better. Then I can find its derivative. The derivative of this, or dy dx, then based off this proposed solution, the derivative of the right-hand side should be, let's see, by the chain rule here, this should be 3c e to the 3x. And the derivative of minus 1 is just 0. So to check that, that this is in fact a solution, I'm going to plug in y in for y. I'm going to plug in dy dx in for dy dx and show that this equation, that this differential equation is balanced. So let's see. Dy dx is equal to this expression. So I'm going to substitute that in, 3c e to the 3x minus 3 times what y is. Well, it turns out that y, we just showed, this is our proposed solution for y. So I'll substitute that in, c e to the 3x minus 1. And this, if this is true, then this should be equal to 3. And what do you know? It turns out that if I distribute a minus 3 to each of these things, I get 3c e to the 3x minus 3c e to the 3x minus 3 times minus 1 is plus 1, and this equals 3. So, oh, not plus 1, but plus 3. And what do you know? Cancel, cancel, 3 equals 3. Yes, this is a solution. For part B, I'd like to show sketch the solutions for various values of c, plus or minus 1, plus or minus 2, and plus or minus 3. You can and should do this on your graphing calculator. There's not really a good reason why you would do this by hand. I'm going to use Desmos because, well, that's what I have open and on my computer, but your graphing calculator and a table of values to get a sketch on paper will work just well. So just to show completeness, for completeness sake, here's a 1 plus or minus 1. Unsurprisingly, they're reflections of each other. Plus or minus 2, and plus or minus 3. If you want to graph all of them, here we go. Okay, let's do something more exciting here. Let's find a particular solution that passes through this point. This means we need to figure out what is. This means we need to find c. We need to find the value of c for this proposed solution. That's not so bad. We have the solution, or this proposed solution here. So I'm going to substitute in x is 0, y is 2 into the solution. I'm going to solve this equation for c. And then I'll have my particular solution, meaning I'll substitute in that value in for this equation. So I know that in this, if for the point 0, 2, that y is 2. I don't know what c is, but I know that x is 0 minus 1. Or maybe better yet, that 2 equals c e to the 0 is 1 minus 1. Add 1 to both sides, you get c equals 3. Lastly, I'm going to find the equation of the tangent to the particular solution at 0, 2. I know that the particular solution is now, this tells me that the particular solution is y equals 3 e to the 3x minus 1. So I need to find the equation that's tangent to this curve that passes through the point 0, 2. Tangent, finding the equation of tangent line, the slope of a tangent line is the derivative. So I think I need to find the derivative of this function. I need to find the derivative of the function at 0, 2, find its value, and that will be the slope. So if I could find the dy, what dy dx is at 0, 2, that would be my slope of this tangent line. And my handwriting is particularly bad, but I hope we can figure this out. How do we find the derivative? Well, we have a differential equation. We know that the differential equation that satisfies this is well, we could use either, really. We could use either the derivative of y, or we have a differential equation already that's solved for dy dx up here. And I'm going to use this to help to solve this. So I know that dy dx is equal, dy dx minus 3y equals 3. So I know that dy dx minus 3y is equal to 3. Or better yet, that the slope is equal to 3y plus 3. At the point 0, 2, I would, everywhere I see an x in this formula, I'd plug in 0, and everywhere I see a y, I'd plug in 2. In particular, there are no x's, but there is a y, 2. So I think this tells me that the slope is equal to 3 times 2 plus 3, which is 6 plus 3, which is 9. So the slope of my tangent line is 9. It passes through the point 0, 2. So in point slope form, my line would be y minus 2 is equal to the slope times x minus 0. Or maybe in slope-intercept form, this is y is equal to 9x plus 2. Just as a check, I already have this input on the Desmos. So maybe we'll see, let's double check to make sure that for the curve when c is 3, that this is actually tangent. And I'm pretty sure it's going to be. Graph on Desmos again. I'm going to turn off all of these graphs except for the one where c is 3. And I have the tangent line, our proposed tangent line already programmed in. And with any luck, it will in fact be tangent at the point 0, 2. And what do you know? They intersect at 0, 2 and is pretty clearly tangent.